In 1948, an open hearth melter in Youngstown, Ohio, could tell the temperature of molten steel within 20 degrees just by looking at it. No pyrometer, no computer, just his eyes. Today, a $1 million sensor array does the same job. Worse, some old-timers say. Number 11 on this list saved more lives than any safety system ever installed. And number 3, modern engineers admit no algorithm has ever duplicated it. These 20 skills built America. Hit that subscribe button and let us count them down. Number 20. Spark testing at the grinder. Before spectrometers, before X-ray fluorescence guns, a mill worker identified steel with a grinding wheel and his own 2 eyes. He would press a piece of unknown metal against the spinning stone and read the shower of sparks like a fortune teller reads tea leaves. Low-carbon steel through long yellow streamers. High-carbon steel exploded into bursting white stars, branching and splitting like fireworks. Tool steel with tungsten glowed a dull red at the tips. A skilled man at Bethlehem Steel in the 1950s could sort mixed scrap into 6 or 7 grades in an afternoon and get it right within a few points of carbon. He earned maybe $1.65 an hour doing it. Mix the wrong scrap into a heat, and you could ruin 200 tons of steel worth more than his annual wages. The spark test was never in a textbook. It passed from man to man in the corners of the scrapyard. Modern handheld analyzers cost $15,000 and still get fooled by coatings and surface rust. The old spark reader just ground a little deeper and looked again. When the last of those men retired, the mills bought machines. The machines have never worked in the rain. The men did. Number 19. The inspector's eye. Steel bar came off the finishing stands moving faster than a man could run, glowing orange, throwing scale. And a bar inspector stood beside it, hour after hour, catching defects that lasted a fraction of a second in his vision. A seam looked like a hairline of shadow. A lap looked like a fold in wet cloth. A scab looked like a fleck of dandruff on a shoulder. Miss one, and that flaw traveled into an axle, a rail, a bridge pin, and somewhere down the line, something broke and somebody died. At Republic Steel in Cleveland, inspectors trained for 2 years before anyone trusted them alone on a shift. The best of them developed something researchers later studied and could not explain. They saw defects before they consciously registered them. Their hand hit the marking paint before their brain finished the thought. Machine vision systems today scan bar with lasers and cameras at thousands of frames per second. They still flag false positives by the hundreds and still miss the shallow seam that a man named Stanley or Walter or Ezekiel would have caught without breaking his conversation about the Indians game. The camera sees light. The inspector saw trouble. Those are not the same thing, and no engineer has ever written code for the difference. Number 18. The hand signal language. A steel mill in 1955 was louder than a battlefield. Rolling stands screamed, furnaces roared. You could stand a foot from another man and not hear him shout. So the mills developed a complete silent language, and every worker was fluent. A raised fist meant, "Stop everything now." Fingers walking across a palm told the craneman to travel slow. A thumb jerked toward the chest meant, "Bring it to me." 2 taps on the hard hat meant danger overhead. The vocabulary ran to dozens of signs, and it varied from mill to mill like a dialect. A man transferring from Gary Works to Sparrows Point had to learn the local accent. What made it a skill, and not just a code, was the timing. A hooker guiding a 20-ton ladle of molten iron gave signals a half-second before they were needed, reading the load's swing, the crane's momentum, the craneman's habits. He conducted an orchestra of moving steel with his hands. Radios eventually came, then cameras, then automated cranes. But ask any old-timer, and he will tell you, the radio made men lazy and the mill more dangerous. When your life depended on watching each other, everybody watched. Nothing has replaced that. Number 17. Rigging by eye. Before a load left the ground, somebody had to answer a question with no room for error. Where is the center of gravity? A chainman at U.S. Steel's Homestead Works could look at a 40-foot beam, an odd-shaped casting, a bundle of unequal plates, and place his chains within inches of perfect balance. First try. He judged weight by looking. This casting is about 11 tons, and he judged it close enough that the crane's gauge rarely surprised him. There was mathematics buried in the skill, but the man never saw an equation. He saw thickness, taper, hollow sections, the way water pooled on top after rain, and his hands knew where the chains went. Get it wrong, and a load shifted in midair, chains snapped like rifle shots, and men beneath it had 2 seconds to live. In 1952, riggers earned around $2 an hour, and the good ones were treated like surgeons. Today, there are load calculation apps and engineered lift plans for anything over a few tons. And still, on job sites everywhere, when something odd needs to fly, the crew looks around for the oldest rigger on the ground and asks him where to hook it. The software gives an answer. The old man gives the right one. Number 16. Catching hot steel by hand. This is the skill that sounds like a lie. In the old hand mills, sheet mills in the Monongahela Valley, rod mills across Ohio, steel bar came shooting out of the rolls glowing yellow hot, moving fast, and a man called a catcher grabbed it with long tongs, whipped it around his own body, and fed it back into the next pass. Rod catchers looped snakes of red-hot steel around themselves a dozen times a minute, standing inside a moving coil of metal at 2,000 degrees. One stumble, one slow reaction, one bad grip, and the bar went through him instead of around him. Catchers were the athletes of the industry, recruited the way colleges recruit quarterbacks, and a first-rate catcher in 1910 earned more than the town doctor. Continuous mills finally ended the trade. Repeaters and mechanical loops took the bar out of human hands. But engineers who designed those machines studied film of catchers frame by frame, trying to copy the timing. They got machines that do the job. They never got that impossible casual grace, a man in a wool shirt dancing with a serpent made of fire. Number 15. Setting the rolls by feel. A roller in a blooming mill controlled screws that adjusted the gap between rolls weighing tons apiece. His product had to hit dimensions within a few thousandths of an inch, thinner than a human hair, and he had no digital readout. He had a wheel in his hands, the sound of the mill in his ears, and the feel of the machine coming up through his boots. He listened to the bite as steel entered the rolls. A clean bite had a particular thump. Too much draft, and the mill groaned. Too little, and the pass whispered. He watched the bar's shape as it emerged, read the curl and the spread, and corrected the next pass before measurement confirmed what he already knew. Rollers at Jones and Laughlin in Aliquippa served apprenticeships that ran a decade before they got the wheel. In 1956, a roller on incentive pay could clear $3 an hour. Elite money, more than most foremen. Automatic gauge control arrived in the 1960s, hydraulic screws and computers chasing tolerance. And here is the strange part. The computers were tuned using data recorded from the best human rollers, because nobody could model what they did any other way. The machine holds the number now, but the number came from a man. First pattern break. Here is what nobody tells you about automation. When the mills computerized in the 1970s and 1980s, engineers assumed the skills on this list were just measurements waiting to be digitized. Temperature is a number, thickness is a number, carbon is a number. Then they discovered something that embarrassed an entire generation of experts. The old workers were not measuring one thing. They were measuring 50 things at once: sound, color, smell, vibration, timing, history, and blending them into a single judgment no sensor suite could match. Researchers call it tacit knowledge now, and they write papers about it. The men who had it called it knowing your job. Most of them were dead before anyone thought to ask how they did it. What was lost was not data. It was a way of thinking that took 20 years to build and one retirement party to destroy. Number 14. Reading the brick. Every furnace, every ladle, Every vessel that touched molten steel was lined with refractory brick, and that brick was always dying. The question was, how fast? A ladle liner at Inland Steel in East Chicago could look into an empty, glowing ladle and tell you whether it would survive 3 more heats or fail on the next one, reading the color of the hot brick, the wear line, the tiny spalls that meant deep cracks behind them. Guess wrong in one direction, and you wasted brick, tearing out lining with life still in it. Guess wrong in the other direction, and molten steel found the shell. A breakout, 3,000 degrees of liquid metal pouring onto a wet floor. An explosion that could level the pit. The men who patched ladles worked inside them while they were still hot enough to bake bread, slapping wet dolomite onto the walls, and they knew each ladle by name and personality. Number 7 always washed out at the slag line. Number 12 had a soft spot near the nozzle. Laser scanners map refractory thickness today, precise to the millimeter. They still cannot tell you what the old liner could, not how thick the brick is, but how long it will hold. Number 13. The millwright's ear. A steel mill never stopped talking, and the millwright understood every word. Walking his rounds through the drive rooms and roll stands, he heard 1,000 overlapping sounds, and the one sound that did not belong. A bearing beginning to fail whispered before it screamed. A gear with a cracked tooth clicked once per revolution, buried under the roar, and the millwright's head turned toward it like a hunting dog. Men at Youngstown Sheet and Tube diagnosed machinery by pressing a screwdriver against a housing and putting the handle to the skull, using their own bones as a stethoscope. They caught failures days early, scheduled the repair for Sunday, and the mill never lost an hour. What they prevented never appeared in any record, because prevented disasters leave no paperwork. Vibration analysis exists now, accelerometers, spectrum plots, software subscriptions that cost more per year than a 1950s millwright earned in a decade. But every plant still has stories about the day the system showed green across the board, and some gray-haired mechanic stopped mid-stride, frowned, and said, "Shut it down. That does not sound right." And he was right. He was always right. Nobody can explain how, least of all him. Number 12. The heater's judgment. Before a steel ingot could be rolled, it had to be soaked, buried in a pit of fire until it reached rolling temperature all the way through, not just at the skin. And here was the problem. You cannot see the middle of a solid block of steel. The heater did anyway. He looked down into the soaking pit through blue glasses at ingots glowing like the surface of the sun, and he judged their readiness by uniformity of color, by how shadows behaved on the surface, by the subtle difference between an ingot that glowed and an ingot that had become glow, indistinguishable from the fire around it. Washed out, the old-timers called it. Pull an ingot cold in the center, and it could split the rolls, machinery worth more than every house on his street. Pull it late, and you burned fuel, burned steel, burned the schedule. Heaters at Edgar Thomson Works in Braddock ran a dozen pits at once, tracking every ingot's history in their heads. When it charged, how hot it arrived, which pit ran lean. Thermocouples and computer track and trace models replaced them. The models still get confused when the sequence breaks. The heater never did. His model updated itself every time he blinked. Number 11. Feeling trouble before it happened. This is the one that saved more lives than any invention. Ask survivors of the old mills how they lasted 30 years around molten metal, moving cranes, and machines that could not feel pain, and they all say a version of the same thing. You develop a sense. A ladle about to spit gave off a sound half a second early, a fat pop in the slag. A furnace about to slip changed its breathing. Wet scrap in a charge, the deadliest mistake in the industry because water under molten steel becomes an instant bomb, announced itself in a smell, a hiss, a wrongness that veteran melters caught while new men noticed nothing. Old workers pulled rookies back from spots on the floor for no reason the rookie could see, and 2 seconds later, that spot was covered in sparks. They felt a crane's shadow without looking up. Scientists studying firefighters found the same phenomenon and called it recognition-primed decision-making, the brain pattern matching faster than conscious thought. The Mills called it mill sense, and they knew the terrible arithmetic behind it. You learned it from close calls, or from men who never got the chance to pass theirs on. No sensor has it. No sensor ever will. Sensors detect what engineers predicted. Mill sense detected what nobody predicted, and that is the only kind of danger that kills. Second pattern break. Here is the part that should make you angry. When the mills closed, Youngstown in 1977, Homestead in 1986, and dozens more through the 1980s, nobody debriefed these men. Nobody sat them down with a tape recorder and asked how they read a heat or balanced a load or heard a bearing die. Companies documented the equipment down to the last bolt and let a century of human expertise walk out the gate carrying a lunch pail. Some of these men had knowledge that existed nowhere else on Earth. It lived in their hands and nowhere else. Universities now spend millions trying to capture expert operator knowledge in industries that still exist. For American Steel, that effort came 40 years too late. The library burned, and we did not even smell the smoke. Number 10. Reading the slag. Floating on top of every heat of steel was a layer of molten slag, and to a first helper on the open hearth, that slag was a written report. He dipped a steel rod into it, pulled out a sample, and watched it cool on the rod like candle wax. The color told him the oxidation state. Black and glassy meant one thing, brown and stony another. A slag that cooled the color of coffee with cream meant the heat was coming into line. The way it strung when he tipped the rod told him the lime balance. The way it snapped or crumbled told him more. From a smear of frozen slag, a good first helper knew the invisible chemistry of 200 tons of liquid steel beneath it and knew exactly what shovel load of what material to throw at the problem. Modern shops send slag samples to X-ray labs and wait minutes for a printout. The first helper's lab result took 8 seconds and required equipment worth 40 cents. On chemistry that mattered, the printouts mostly told him what he already knew. Number 9. Teaming the ingot. When a heat was ready, it poured from the ladle into ingot molds through a nozzle in the ladle's bottom, and the man controlling that pour was called a steel pourer, and his job was closer to art than anyone admitted. He worked a stopper rod, a lever controlling a plug in white-hot liquid, and he had to hold the stream steady, centered, and at exactly the right rate. Pour too fast and steel splashed the mold walls, freezing into scabs that ruined the surface of everything rolled from that ingot. Too slow and the steel skinned over, folding cold laps into the metal. The pourer read the stream itself. A clean pour ran smooth and quiet, almost like honey. A stream that sparked and spat told him the steel was wild, and he adjusted on instinct. He judged the moment to cap each mold and moved to the next without ever fully closing the stream. 70 tons passed through his hands in 20 minutes. Continuous casting made the ingot pourer extinct. Steel now flows into a machine that never gets tired. But the machine also never poured the strange small heats, the experimental alloys, the awkward jobs. For those, foundries to this day quietly go looking for an old man who remembers. Number 8. The crane operator's touch. 50 feet above the floor, in a cab hot enough to cook in, the overhead crane man moved loads that outweighed locomotives and set them down like sleeping infants. A hot metal crane man at Gary Works carried ladles of liquid iron across a working floor with men underneath, and his cargo behaved like a giant bowl of soup. Start too hard and it sloshed, stop too hard and it swung, and a slosh from a ladle meant fire raining on the crew below. So he learned to move without moving, feathering controllers, killing swing with countertaps timed to the pendulum, landing 100 tons within a quarter-inch of a chalk mark he could barely see. The best cranemen threaded ingots into pit covers with clearances measured in fingers, all day, every day, judging distance from an angle no human eye was designed for. In 1950, he made around $2 an hour, and every man on the floor knew his name, because every man lived inside his judgment for 8 hours a turn. Automated cranes run warehouses now. Steel shops tried them. Molten metal, drifting loads, and human floors sent most plants straight back to the man in the cab. Some jobs, the computer politely declined. Number 7. The keeper's cast. At the bottom of a blast furnace, a 14-story volcano that ran for years without stopping, worked the keeper, and his job was to know when to let the volcano bleed. Iron and slag pooled in the hearth, invisible behind feet of brick, and the keeper judged the level by signs no gauge measured: the glow through the tuyere peep sights, the sound of the blast, the furnace's pressure, the time since last cast, the way she had been driving all shift. Men spoke of furnaces as women with moods. Each one had habits, and the keeper knew them the way a husband of 40 years knows a footstep. When he called the cast, his crew drilled the tap hole, and a river of iron came out at 2,700 degrees, running down sand-lined trenches the keeper had shaped by hand like a farmer laying irrigation. Wait too long, and iron rose into the tuyeres and wrecked them. Cast too early, and you disturbed the furnace's rhythm for a day. Modern furnaces have hearth models, thermocouple arrays, and automated drills. And still, when a furnace starts acting strange, control rooms fill with retired keepers brought back as consultants at triple their old wages, standing at the peep site, squinting, saying, "Give her 20 more minutes. She is not ready." Number 6. Scarfing by hand. Steel came out of the mill wearing its mistakes on its skin, cracks, seams, patches of bad surface, and the men who removed them were called scarfers and chippers. A hand scarfer walked the slab yard with an oxygen torch that roared like a jet, and he burned away defects in shallow, controlled washes, steering a puddle of burning steel with wrist movements measured in millimeters. Go too shallow and the crack survived, hiding, waiting to open up in some customer's forging press. Go too deep, and he gouged the slab, scrapping value with every pass. He judged depth by the color of the burn and the behavior of the sparks, crouched over metal still hot from the pits, in leather that smoked. It was brutal, dirty, low-glory work, and it required the fine motor control of an engraver. Machine scarfers exist, great automated flame boxes that burn the entire surface of a slab as it passes. They work by removing everything, good steel and bad, because the machine cannot tell the difference. The hand scarfer removed only the flaw. One process is surgery, the other is amputation. Guess which one we kept? Number 5. Making bottom. After every heat, the floor of an open hearth furnace, the basin that held 200 tons of liquid steel, needed repair, and repairing it was a craft with no written manual anywhere on Earth. The crew threw shovel loads of dolomite and magnesite into a furnace still glowing at welding heat, aiming through the doors at low spots 20 feet away, and the material had to land exactly where the wear was, fritting onto the hot surface in even layers. A first helper read the bottom through blue glass, mapped every hollow in his memory, and directed the throws like an artillery spotter. Build the bottom wrong, a hollow here, a soft patch there, and steel found the weakness, drilled into it heat after heat, and one day cut through to the ground in a breakout that could kill the furnace and the men serving it. Good bottom makers were traded between shops like ball players. The skill took years to learn because you could only practice on a real furnace, with real consequences, between real heats, with a foreman timing you. When the basic oxygen process replaced the open hearth in the 1960s and 70s, bottom making died in a single decade. There is no machine for it. There was never a machine for it. There are just a few men left alive who did it, and every one of them is past 80. Third pattern break. Notice something about these last few skills. None of them show up in a job description. Bottom making was filed under second helper duties. Reading slag was just part of the turn. The companies never fully understood what their own workers knew, which is exactly why they believed machines could replace them cheaply. The machine replaced the job title. It did not replace the knowledge, because the knowledge was never written down where the accountants could see it. Mills automated, and, for years, quality problems went up. Breakouts went up. The new systems failed at everything the old workers had silently prevented and nobody had ever counted. You do not know what a man is worth until he retires and 3 departments quietly stop functioning. American Steel learned that lesson the hard way, one closed mill at a time. Number 4. Reading the flame. An open hearth furnace burned gas or oil in a great swirling flame above the steel, and the melter tuned that flame the way a conductor tunes an orchestra. Too much air, and the flame ran short, sharp, and white, hot but wasteful, eating the roof brick. Too much fuel, and it ran long, lazy, and smoky, licking heat uselessly out the flues. The perfect flame had a color and a body the melter knew on sight. Luminous, muscular, sweeping down to brush the bath itself. Every 15 or 20 minutes the furnace reversed, air and gas swapping ends to reclaim heat from checker brick. And the melter timed the reversal by the sound of the burn and the color at the ports, keeping the furnace breathing like a long-distance runner. Get the rhythm wrong, and heat slowed by hours, and hours were thousands of dollars. Combustion is fully computerized now. Oxygen probes, flow meters, optimization software. Engineers who tested the software against records of the best hand-fired furnaces of the 1950s found something uncomfortable. On their best days, the old melters matched it. With their eyes. With no meters at all. The software runs a model of physics. The melter ran a model of that furnace. Number 3. The fracture test. Here is the skill modern engineers openly admit they cannot duplicate. Take a sample of steel, cool it, break it in two, and look at the freshly broken face. To you, it is gray metal. To an old-time melter or blacksmith-trained millman, that broken face was a printed chemical analysis. The size and shine of the crystal grains told him the carbon content, not roughly, but to within a few hundredths of a percent. A fine, silky fracture meant one grade, a bright, coarse sparkle another. He could see overheating in the grain. He could see brittleness. In the days before chemistry labs, entire mills shipped steel graded almost entirely by fracture, and railroads bet human lives on those readings, and the readings held. Researchers put fracture graders up against laboratory analysis and recorded accuracy that made no sense on paper. The knowledge was pattern recognition trained on tens of thousands of samples, calibrated by consequence. Today, a spectrometer does it in 30 seconds, and does it well. But the spectrometer needs power, calibration gas, a clean sample, and a technician. The old man needed a hammer and daylight. One of those systems fails in a crisis. The other one was a crisis skill to begin with. Number 2. Fixing anything with nothing. A steel mill could not stop. When something broke at 3 a.m. on a Sunday, and it always broke at 3 a.m. on a Sunday, there was no calling the manufacturer, no overnight part, no downtime budget. There was a millwright, a welder, a machinist, and a pile of scrap, and the mill ran again by morning. These men remachined bearings on lathes older than they were. They built replacement parts from drawings that existed only in their memory of the part that just failed. They welded cracked housings that the book said could not be welded, using tricks, peening, preheating with the furnace's own waste heat, cooling rates judged by spit sizzling on metal that came from 30 years of Sundays. At Weirton Steel, crews kept machines from the 1920s running into the 1990s, decades past the death of every company that had built them. This was not maintenance, it was resurrection, performed on schedule, in the dark, for $2.50 an hour. Modern plants run on scheduled replacement and manufacturer service contracts, and when the contractor cannot come, the line waits. The old mill never waited. Somewhere in every plant that survived, there is still one man like this, and management prays daily that he does not retire before his replacement is born. Number 1. The melter's call. Everything on this list flowed into one moment. 200 tons of steel boiled in the furnace, worth a fortune, wanted by a customer to an exact chemistry. And one man, the melter, had to say the word. She's ready. Tap her. He made that call by pulling a test spoon of liquid steel and pouring it, watching how it sparked, how it ran, how the sample sucked in or puffed up as it froze in the mold. He made it by the way the bath boiled. A heavy, rolling boil meant carbon still burning. A quieting bath meant the drop was near. He made it by the slag on his rod, the color through his blue glasses, the sound of the furnace, the hours on the clock, and 40 years of heats stored in his head. Temperature within 20 degrees. Carbon within points. No instruments. Tap high and the heat was ruined in the ladle. Tap low and you cooked it back at ruinous cost. The melter carried the value of a house in every judgment, 8 times a turn, and the whole shop moved on his word. He was, by every definition that matters, a human sensor array wired to a human computer, running software written by experience and debugged by fire. We built machines that measure what he measured. We never built one that knows what he knew. That is not nostalgia. That is the honest engineering assessment of everyone who has tried. So here is my challenge. If your father, your grandfather, your uncle, your neighbor worked steel, Pittsburgh, Youngstown, Gary, Bethlehem, Birmingham, anywhere, ask them about one skill on this list before it is too late. Ask about the sounds. Ask about the flame. Then come back and tell me what they said, because I want those stories in the comments where they cannot be lost. Tell me which skill amazed you most. My money is on the fracture test, but the catchers might steal it. These were not just jobs. They were a form of genius we melted down and never recast. The men knew. Now you know too.